Okay, I think it's almost time to start. So welcome everyone to the first research track parallel session. And this session is on recommender systems. And we have 5 papers in this track. Now, each paper has a 15-minute video, which is already recorded, which we will be playing back. And then we have 3 minutes for questions. You can answer questions at any time you want during the talk on the chat. And at the end of the talk, we will ask the questions. So the very first talk is on group recommendation with latent voting mechanism. And the presenter is Lei Guo, who is working as an associate professor and master supervisor at Shandong Normal University, China. Lei is with us, and I request the student volunteer to play the video now.
Hello everyone, I'm Yu Zheng from Tsinghua University. It's my great honor to present our work, Price-Aware Recommendation with Graph Convolutional Networks.
Sorry about that. Yeah, it should be up in just a second.
It's a joint work of Tsinghua University.
Can you hear the video?
Hello everyone, I'm Yu Zheng from Tsinghua University.
What? That's the wrong video.
That's the wrong video. Oh.
I think the first one is group recommendation. Unless I goofed up. I'm sorry if I. Yeah, no, that is the first one, 198.
Let me check.
Hello.
Okay.
Hello, everyone. This is Lei Guo from Shandong Normal University. This work is completed during my visit to the University of Queensland, and my supervisor is Professor Hong Zhi.
Sorry, we are seeing the wrong video. We're hearing the audio, but the video is wrong. Something is messed up. We just start again.
Okay. Let me check. Sorry for the mistake. So the first one will be group recommendation with the latent voting mechanism.
Yes. Paper 198. Yeah. 198 go.
This one.
This is Lei Guo from Shandong Normal University. This work is completed during my visit to the University of Queensland, and my supervisor is Professor Hong Zhi. This work is about how to conduct group recommendation with the latent voting mechanism. Nowadays, owing to the popularity of online to offline platforms, it becomes convenient and easy for a group of people to find a wide range of suitable activities to attend. For example, a group of friends can work together to plan a trip, find a restaurant, or attend a party. Compared with traditional recommendation system, which aims to provide the recommendations for a single user, group recommendation is to provide recommendations for a group of users. Depending on whether groups have stable members, groups can be characterized as persistent groups and occasional groups. Persistent groups refer to relatively static groups with stable members and sufficient group atom interactions. Occasional groups often refer to ad hoc formed groups whose members might join them for the first time, such as groups established for users who attend a social party. As occasional group is more general and realistic, we focus on developing the recommended systems for occasional groups in this work. Here is the existing works. For persistent groups, due to the sufficient group atom interaction records, we can just treat each persistent group as a virtual user and apply existing recommendation methods designed for individual users to this type of group. But for occasional groups, as groups are formed occasionally, there are two types of challenges. First, as only limited group atom interactions are available, traditional methods cannot be directly applied. Second, the decision-making process is rather dynamic. Making a decision within occasional groups is more complicated. Here are typical existing works for occasional groups. The mainstream research for occasional groups focuses on leveraging aggregation-based approaches, that is, late aggregation methods and early aggregation methods. Late aggregation methods first identify the best items for each group member, and then aggregate each group member's preference to select the best item for the group, such as average satisfaction, least misery, and maximum pleasure. Although late aggregation-based methods are simple and intuitive, there are still some limitations for the above methods. That is, they are static, heuristic, and predefined. And due to that, they are too simple to model the real and complex process of group decision-making. Another type of method is early aggregation-based method. In this category, these methods first aggregate group members' preferences as a group preference and then identify the best item for the group. Typical methods in this category include probabilistic generative models and neural network-based method. Probabilistic generative models capture the item selection process of a group with a probabilistic model, such as PIT and COM. Neural network-based methods utilize an attention-based neural network to aggregate group members' preferences. For example, agree and SIGR. However, all the above existing methods mainly focus on modeling the contributions of different members, and they fail to model the interactions among group members. But in real world, when forming a consensus within a group, each member may discuss with others to form his or her own opinion. Moreover, this process can be rather dynamic. First, a member may apply different rules and exhibit different influence in choosing items of different types. Moreover, a member may change his or her opinion within other members' selection. Finally, a member's opinion may be affected by his or her friends. Based on the above observations, we view the decision-making process as a multiple voting process by the following steps. In the first step, for every group with L group members, we first divide each group into L subgroups, and in each subgroup, users will first exchange their opinions with their friends to reach consensus with them. And then each user votes to nominate certain experts on the current topic as the main decision makers. Finally, the item preferred by the most voted users will be treated as the final group decision. This is the overall framework of our method. To model the above decision-making process, we introduce the self-attention network to simulate the L sub-voting processes. To overcome the specific issue of group atom interactions, we exploit a joint training method to enhance group atom training process. To enhance the user repetitions from their historical interactions, we use two types of aggregation methods to learn user features from different feature spaces. This is the overview of our framework, which consists of three components, that is, the voting schema modeling, user modeling, and the joint training method. In the following, I will introduce each of them separately. The first is the voting schema modeling component. As in the real world, each user has two types of characteristics, that is, intrinsic characteristics, and the characteristics in the views of other group members. We divide each group into L subgroups, that is, the S user and the S subvoting group. To learn the S user's two types of characteristics, we transform the latent features of the S subvoting group plus user UI from K-1 layer through linear projections, and then we can get the corresponding queries, keys, and values, which will be further used to calculate the interaction weight among group members. To simulate how user UI exchange his or her opinions with others, we compute the dot product attention between UI and other subgroup members. The dot product between UI and him or herself indicates how much UI insists on her or his own opinions when discussing with other group members. Then, the repetition of a subgroup after discussing with user UI is defined as the weighted sum of the values of all the users within a subgroup and denoted by ZI. As users are social animals, we often turn to friends for recommendations. The interactions with friends are also the key factors that affect our decision. To model the social dependencies, we place a social bias matrix S to mask the dot product attention, where S controls whether the attention schema will be applied to the user pair. The value of the matrix S is defined by the following rules. That is, when user UI and UG are not friends, the value of S will be set as negative infinity. Otherwise, S will be set as 0. The right table is an example where only user 1 and user 3 have social connections. This is the voting schema of our proposed group assay method. Similar to the settings in the transformer, the output of each subgroup is then fed into the their norm and feed-forward neural network. And finally, we use XU to denote the output of a subgroup. The repetitions of all the subgroups are further aggregated by an attention network and use SG to denote the final repetition of a group. The attention weight is parameterized by a two-layer neural network. To alleviate the sparsity issue of group atom interactions, we enhance the user repetitions by using two types of aggregation methods from two different species, that is, atom aggregation and social aggregation. Atom aggregation is to learn user latent factor by aggregating the information of the atoms that the target user has interacted with. The social aggregation is to aggregate the users that have social connection with the target user. Given the embeddings of the target group, users, and atom, we can make predictions for both groups and users, where pairwise loss function is exploited. As we have mentioned before, it's quite possible that an occasional group contains members who have never attended group activities. The sparsity of group atom interaction also makes the learned embeddings of users and atoms unreliable. To overcome the above challenges, we jointly learn all the parameters from the interaction data in an end-to-end manner. To evaluate our proposed method, we explore two large-scale datasets for occasional group recommendation, that is, EOP and domain event datasets. In these two datasets, a set of users are assumed to be a group if they are connected on the social network and visit the same restaurant at the same time or attend the same event. We randomly select 80% of the data as training set and the remaining as a test set. Since it is time-consuming to rank all items for each user and group, we follow the schema used in CHO and its work. That is, we randomly select 100 items that have never been interacted by the test user or group as a candidate set. Each ranked list is evaluated by HR and AGG. We compare our method with the following baselines. That is, the recently proposed SIGGRE and AGGREGATION method, and also the variance of our proposed group assay method. We also compare our method with 3 aggregation-based strategies, that is, group average, group least misery, and group maximum pleasure. This is recommendation performance of our proposed method. From these results, we can see that our group assay method achieves the best performance on 2 datasets for both recommendation tasks. This result demonstrates the positive effects of the social self-attention network in aggregating the preferences of group members and the joint training method in overcoming the sparsity issue of the group item interaction data. To understand the importance of the social self-attention and user modeling components, we compare group assay with its 4 variants, that is group A, group S, group I, and group F. From the experimental results, we can see that group assay significantly outperforms other 4 methods, showing that both self-attention, social self-attention, and the user modeling components are beneficial to the group decision-making. To evaluate the effectiveness of the user item interaction data and the joint training technique, we compare group assay with group G. From the results, we can observe that group assay consistently outperforms group G in both datasets. This result demonstrates the importance of training group assay with user item interaction data to address the corresponding sparsity issue. To be concluded, in this work, we propose a novel group self-attention recommender for occasional group recommendation. To model the interactions among group members, we viewed the formation of a group consensus as a multi-voting process, and a social self-attention network was proposed. To enhance the user's individual representation, 2 types of aggregation methods were developed to leverage items and users that are related to him or her. To overcome the sparsity issue of groups activity data, 2 model optimization approaches were trained jointly in an end-to-end manner. That's all. Thanks for your attention.
Thank you very much. We'll upload virtually. You can't hear us because everybody is on mute. We have time for a few questions. I see one question already up from Yuan, who asked it privately, but Yuan, why don't you unmute yourself and ask the question?
Hi, when you see that you select 100 items users never interacted, is it to simulate the cold start scenario?
No, we just want to reduce the complexity of the testing method, because if when you test the performance, if you rank all the items, it's time consuming. So we just randomly select 100 items as a candidate set. That's also the method used in other papers. So we just follow their method.
Okay, thank you.
Lax has a question. Lax, unmute yourself and go ahead and ask it.
Yes, can you hear?
Lakshman.
Yeah.
Yes.
Yeah, great. Thanks for the talk. I don't recall seeing a comparison in your evaluation with traditional group recommendation algorithms. So how do you think your self-attention based group recommendation compare with the previous work, which is conventional, not using deep neural networks, but traditional approaches, what you call heuristic based approaches?
We just mentioned in our paper because some traditional, because our method is proposed for occasional groups. So we just want to compare our method with the method that proposed for occasional groups, and the method that not use deep neural networks has been evaluated in other papers such as AGGREGATION and SIGGER. So we don't compare them because they have been defeated in their paper in all their datasets. So we don't compare with them in our papers. Thank you.
Okay, thank you very much. We don't have time for any more questions. We can move on to the next talk. Yang, as the host, can you switch over? So while that comes up, let me introduce the speaker and the paper. The paper title is Price-Aware Recommendation with Graph Convolutional Networks, paper number 275. And the presenter is Yu Zheng, who is a PhD student from Data Science and Intelligence Lab of Tsinghua University. The talk is up, so let's get started.
Hello, everyone. I'm Yu Zheng from Tsinghua University. It's my great honor to present our work, Price-Aware Recommendation with Graph Convolutional Networks. This is a joint work of Tsinghua University and University of Science and Technology of China. First, let me introduce the background of this work. When the items in the recommendation system come with an economic cost, it becomes more complicated, since the price of the item will directly determine whether a user is willing to pay for that item, so the price feature is an important feature while different from other features. And we believe that the price feature and other features play orthogonal roles in user decision-making process. Specifically, the price feature determines users willing to pay, and other features determines users' interest. Only when an item both matches users' interest and users willing to pay will the user purchase that item. In fact, there are a series of algorithms called attribute-aware recommendation system, which aims at incorporating all kinds of features into collaborative filtering to boost the recommendation accuracy. And the features could be user feature, item feature, or context feature. For example, in YouTube's recommendation system, they incorporate user features and video features into their scoring model to better estimate the watch time of each video. To incorporate price into recommendation system, one trivial idea is to use these existing attribute-aware recommendation models. However, for most existing attribute-aware recommendation systems, different features are treated equally and captured in a generic and unified way. For example, the factorization machines equally treated all the features and map them to the same shared latent space. Another example is Facebook's deep learning recommendation model, and all the features are fed into this model either as dense features or sparse features. As we introduced, the price feature is different from other features, but existing methods are not specially designed for price. Actually, there are two challenges in capturing users' price awareness. The first challenge is users' price awareness is implicit, which means users seldomly speak out their preference or sensitivity on item price, and we can only infer it from what users have purchased. The second challenge is the price awareness depends on product category. That means users are often inconsistent across different categories. For example, a sport lover would have high tolerance on the price of a sport equipment, but not on alcoholic drinks. Here is an example to verify the second challenge. We plot the purchase history of 3 users as a heat map, and each row represents a category and each column represents a price level. In the same category, the purchase items usually concentrate on the same price level or near price levels. But for different categories, the purchase items could be in far-off price levels. That means the second user is inconsistent in the 2 categories. To address the 2 challenges, we propose price-aware user preference modeling, shortened as PUP. The input our interaction matrix are price of items P and category of items C. And the output is the estimated interaction probability given a user-item pair. To address the second challenge, which is category-dependent influence, we propose a 2-branch solution to separately model the 2 aspects. In the global branch, we model price as a global effect representing the user's overall purchasing power, and this branch is unrelated to category. And in the second category branch, we model the category-dependent influence of the price factor. The 2 branches are same and parallel, and each branch is composed of 3 parts: unified graph construction, graph convolutional encoder, and pairwise interaction-based decoder. I will first explain why we use GCN, and then I will introduce the model part by part. The first reason for using GCN is to capture the collaborative filtering effect, which is very important in recommendation. And actually, GCN is the state-of-the-art CF model. The second reason is that there are 4 types of entities, and GCN could learn robust representations for heterogeneous entities. The third reason is price awareness is a kind of high-order similarity, since it could only be inferred from the purchase items, and GCN could model the high-order similarity. Let's turn to the first part, graph construction. There are 4 types of nodes: user, item, price, and category. And there are 3 types of edges. User-item edges stand for the observed user-item interactions. And we also link each item to its corresponding price and category. For ease of modeling, we consider price as categorical variable, so we discretize price within each category using uniform quantization. We addressed the first challenge by using item nodes as the bridge. And the second challenge is addressed by further including category nodes. The second part is graph convolutional encoder. We first use an embedding layer to transform the one-hot ID feature to embedding feature. Then we use a graph convolutional layer to perform embedding propagation and neighbor aggregation. By the graph convolutional encoder, we obtain representations for users, items, prices, and categories. And the challenge 1 is addressed because the price awareness could propagate from price nodes and category nodes to user nodes through item nodes. The last part is pairwise interaction-based decoder. Calculation of the score is similar to factorization machines, and in the global branch we take inner products of user embedding, item embedding, and price embedding. In this branch we omit category embedding. In this branch, we model users' interest and overall purchasing power. In the category branch, we take inner products of user embedding, price embedding, and category embedding, and we ignore item embedding. In this branch, we model users' category-dependent price awareness. Challenge 2 is addressed by separately modeling the global effect and category-dependent effect of price. To attain the final prediction, we combine the two branches with a hyperparameter alpha, which balances between the two aspects. In terms of model training, we follow the semi-supervised graph encoder fashion, which means in the encoding stage, we learn expressive representations for all kinds of nodes, and in the decoding stage, we only focus on reconstructing user item edges and don't care about the other two types of edges because the user item edges is the main task. We use BPR as the loss function. We conduct some experiments to evaluate the performance. We use two real-world datasets of restaurant recommendation and e-commerce recommendation. Statistics of the two datasets are summarized in the table. We use two metrics, recall and NDCG, to evaluate the performance of top K recommendation. We compare our PUP method with these baseline methods. We would like to answer the following research questions. The first question is, how does PUP perform compared with other baseline methods? The second question is, could PUP recommend items which match users' price awareness? And the last question is, could price help recommendation system in cold start scenarios? We first compare the performance of all methods. And we have several observations. The first observation is attribute-aware methods generally outperform trivial CF methods. For example, FM and Deep FM incorporate category and price into the system, and they perform much better than BPR in most cases. So incorporating price into recommendation actually improves accuracy. The second observation is models based on neural networks and graph neural networks achieve better results than other models in most cases. So it is promising to introduce deep models, especially GNN models, into representation learning. The last observation is our proposed PUP achieved the best performance. In spite of overall evaluation, we also conduct user study. We find 4 users who are highly inconsistent across different categories, and they purchase items of high price in non-sensitive category and only purchase cheap items in sensitive category. Then we calculate the average price of the recommended items from the two categories, and we can find the average price for the non-sensitive category is much higher than the sensitive category, so the proposed PUP method could successfully recommend items matching users' price awareness. According to related research, the price feature could be utilized to tackle cold start problem, and here the cold start problem means category cold start, where we recommend items of unexplored categories. There are 2 evaluation protocols, CIR and UCIR. I will introduce the 2 protocols by this example. Suppose there are 7 categories in total. A user explored 3 categories, which are A, B, and C in the training set, and explored a new category E in the test set. In CIR, we recommend from all items of category E. And in UCIR, we recommend from all items of category D, E, F, and G. So UCIR is much more difficult than CIR because the model should first learn to recommend from the correct category, then learns to recommend the right items. Here are the results of different models. The first two are FM and Deep FM, which are not based on graph, and the last three are GCMC, PUP-, and PUP, which are based on graph, and PUP- is a slim version of PUP with the category nodes removed. The first observation is graph-based methods outperform other methods. It's because items of cold start categories are more reachable on the graph, since they are high-order neighbors. The next observation is PUP and PUP- performs better than GCMC. GCMC is a CF method which does not consider price. So if we incorporate price and category into the system, it will help us to better transform from what we learn in the explored category to the cold start categories. Finally, we conclude this work. First, we highlight the significance of incorporating price into recommendation and analyze the two difficulties in capturing price. Second, we propose a GCN-based method named PUP and adopt a two-branch structure which separately models the global and category-dependent effect of the price awareness. And last, our proposed method could recommend items matching users' price awareness and alleviate the cold start problem when recommending items from unexplored categories. Thanks for listening, and here are some contact information of our lab.
Thank you very much. We have time for a few questions. If anyone has questions, please type in the chat window, or you can also unmute yourself and go ahead and ask, since we are a small group.
Okay, this is Lux again. If nobody has questions, then I can ask mine. I don't want to hog this session.
Go ahead, Lux. Nobody else has asked so far.
Okay, so interesting talk, interesting work. So in handling and modeling price, I noticed that you have quantized price. You have binned the price into some categories, let's say, and that necessarily is ad hoc, right? So the question is, have you thought about quote unquote optimally quantizing the prices? So that has got to improve the performance, right? So have you given any thought to this?
Okay, it's a great question. And for e-commerce recommendation, it's common that there will be a small fraction of items with extremely low price and also a small fraction of items with extremely high price. And the large scale of items are in the middle. And in the paper, we have tried different strategies to discretize the price. We try to discretize based on the absolute value of the price, and we also try discretize the price with first ranking all the items within each category and discretize the price according to the rank. And the performance are slightly different from each other. Thank you.
Okay, thank you.
Thank you. Is there any other question? We have time for one question. Okay. Since there don't seem to be any more questions, I think this talk has answered all possible questions, maybe. So it's highly recommended. And thank you. Let's move on to the next talk. Yang, while you start the video, let me introduce the speaker. The next talk is on syndrome-aware herb recommendation with multi-graph convolution network. And it's being presented by Yuan Jin, who is a PhD candidate of East China Normal University. Her major is software engineering, and current research interests mainly includes recommender systems.
Hello everyone, I'm Yuan Jin from East China Normal University. The topic of our paper is herb recommendation. We proposed a syndrome-aware multi-graph convolution network-based herb recommendation approach. This is the outline in my report. First, I introduce some background and related work. Next is our proposed method. The third part is the experimental results. The last is the conclusion. In traditional Chinese medicine, the basis theory is the thinking of holism, which emphasizes the integrity of the human body. The TCM doctors take a three-step therapeutic process. The first is symptom collection. The doctor examines the symptoms of the patient. In this case, the symptoms are night sweat, pale tongue, small and weak pulse, amnesia. The second step is syndrome induction. Corresponding syndromes are determined after an overall analysis of the symptoms. In this case, the main syndrome is deficiency of both spleen and blood. As pale tongue, small and weak pulse can also appear and the spleen fails to govern blood, there is also an alternative option called the spleen fails to govern blood. The last one is the treatment determination. The doctor chooses some herbs as the remedy. Here the herbs are Angelica sinensis, Longan aerial, ginseng, and takhol. The second step, syndrome induction, is very critical for herb recommendation. However, given a single symptom, it can appear under various syndromes, which makes the syndrome induction complex and ambiguous. Actually, given a symptom set, different doctors might give different syndromes. Thus, no standard ground truth exists. In this paper, we define the herb recommendation task as follows. Given a symptom set, recommend a herb set from all herbs. The related work contains two parts. The first is the herb recommendation methods. In topic model-based herb recommendation, TCM prescriptions are documents consisting herbs and symptoms as words. The graph-based herb recommendation methods usually exploit the graph representation learning-based methods. The weak point is that they learn the latent syndrome topic distribution given a single symptom and only model the interaction between one symptom and one herb. Thus, the set information of symptoms is overlooked. Inspired by the above graph-based herb recommendation, we also surveyed the state-of-the-art GNN-based recommender systems. There are many applications to different kinds of graphs. The GNN-based models show convincing performance and high interpretability for the non-Euclidean space graph data. Next is our model. For herb recommendation, we want to highlight the importance of implicit syndrome induction process and to model the interactions between syndromes and herbs. We use the multiple GCNs and MLP techniques. The MLP is used to fuse symptom embeddings into the overall implicit syndrome embedding, and the multiple GCNs in relational data learning is to enrich the relations. Here is our model framework from bottom to top. First, we input the symptom set SC and all herbs H. Through the multigraph embedding layer, we obtain the embeddings for each symptoms and herb. Then, the syndrome induction component will aggregate the embeddings in the symptom set SC to get the implicit syndrome representation, E syndrome. The next step is the E syndrome interacts with the herb embeddings EH to output the probability vector Y hat SC for all herbs from H. Next, we will introduce the multigraph embedding layer in detail. It's designed to obtain expressive representations for all herbs and symptoms. It contains multiple herbs. The bipartite graph convolutional neural network is based on the symptom herb graph, and the synergy graph encoding part is based on the herb graph and the symptom graph. The three graphs is showed in the picture. These two parts are fused to form integrated embeddings. Next, we zoom in the BiPAR GCN part. BiPAR GCN is to capture the intrinsic difference between the two types of nodes. When the type of the target node is symptom, the symptom-oriented GCN is triggered. When the type of target node is herb, the herb-oriented GCN is triggered. In this way, different types of nodes develop their own propagation flexibility. This slide shows the bypass GCN formulation details. In the high-order propagation, we use the average pooling here. Although the two order pairs in the symptom-herb graph are already the herb-herb pairs and the symptom-symptom pairs, however, they don't equal to the concurrent pairs in prescriptions. Here is an example. Given two prescriptions P1 and P2, we can find that H2, H3, H4 is the second-order neighbors of H1 through S1. However, H3 and H4 do not appear with H1 in the same prescription. Thus, it's necessary to additionally construct the herb-herb graph and symptom-symptom graph. During graph construction, we introduce the threshold to control the sparsity of the graph. For example, if HM and HN co-occurred in the prescriptions for more than XH times, then there is an edge between HM and HN. In propagation phase, here we use the add operation instead of the average pooling. The reason is that after our analysis, we found that the symptom herb graph is much denser than the synergy graphs, and the degree descriptions of synergy graphs are smoother than the symptom herb graph. Considering the later fusion of these two parts, we use the add operation here to make these two parts more balanced. After getting embeddings from bypass GCN and SGE parts separately, we use the addition operation to fuse the two parts. To this step, we have constructed a general architecture which can model interactions between two types of objects. After obtaining the embeddings for symptoms and herbs, next we move to the syndrome-aware prediction layer. In this layer, we borrow the nonlinear strengths of MLP to capture the ambiguous and complex syndrome induction process. As this picture shows, we feed all symptoms embeddings in a symptom set into an MLP to induce the overall implicit syndrome representation. During training, we adopt the multi-label classification loss, weighted mean square loss. The weight WI is to tackle the label imbalance problem, which is that the herb frequency distribution is imbalanced. When doing inference, we adopt the greedy strategy to select the top K herbs with the highest probabilities in function G as the recommended herb set. Here is the experimental results. We will show the key results. We use a benchmark TCM dataset, which is publicly available. The metrics are commonly used: precision recall and NDCG. The baseline methods contains one topic model, and the others are GCN-based models. Among them, the heter-GCN adopts the type-based attention mechanism to perform message construction. Here is the overall performance. We can see that SMGCN performs the best, and the topic model almost performs the worst. In addition, SMGCN is superior to heter-GCN, which validates that the multi-graph GCN framework can learn a more flexible and expressive model compared with the unified heterogeneous graph-based GCN. We also conduct the ablation analysis. The experimental results show that the MLP is superior to only employing average pooling, and integrating synergy graph encoding also leads to the further improvement. Here is some key hyperparameters. The first is the threshold, when constructing the synergy graphs. Taking herb graph as an example, we can see that when the threshold XH equals 40, our SMGCN can achieve slightly better performance. We also compared our multi-label loss with the BPR loss. The results show that our multi-label loss outperforms the BPR loss. The reason may be that the multi-label loss computes the distance between the recommended herb set with the ground truth herb set, which evaluates the results from the set view. Here is a herb recommendation case. The table contains 2 prescriptions. For each symptom set, our SMGCN can generate a herb set as the recommendation result. The red bold font indicates the common herbs between our SMGCN generated herbs and the ground truth. The last is the conclusion. We present a syndrome-aware herb recommendation model, which takes implicit syndrome induction into consideration and develop a series of GCNs to learn the symptom embedding and herb embedding from multiple graphs. Thank you for listening. Any questions?
Thank you. We have time for a few questions. Anyone have any questions? You can unmute yourself and ask. I have a question. So it seems that you're making recommendations, which probably is what a doctor would do, but what is the guarantee that what you're doing is correct? I mean, you have some tests which seem to show that it compares well with what somebody has recommended, but even one significant error could be pretty expensive. It could lead to serious problems, right? So how do you guarantee that this is safe?
Yes, our ground truth is from the traditional Chinese medicine prescriptions. Our evaluation is based on the standard prescriptions. And in the future, we also plan to cooperate with TCM doctors to help evaluate our results.
Are there clinical trials and such like to check if these recommendations help or harm or whatever?
Yes, because in the practical clinical process, the different doctors may give different prescriptions. To some extent, the evaluation itself is a bit ambiguous. Thus, we proposed in our model, we just incorporate the syndrome concept as a representation to model the ambiguous and complex in the TCM itself.
Thank you. Are there any other questions?
Yeah, this is Chris Lipton.
Yes,
Quick question, kind of following up on the last one. Wondering, to the herb graph, to what extent does that capture essentially the equivalent of drug-drug interactions, where perhaps you have two things that should not be given together? Is it learning things like that? Are you able to test any of that against expert knowledge on whether you're able to pick up on kind of interactions where two drugs together would not be co-indicated, or two herbs together would not be co-indicated?
Yes, in TCM and also in the Western medicine itself, the drug-drug interaction is important to notice. So we also additionally introduce the herb graph and symptom graph to capture this information.
Is it? I guess my question is, were you able to validate this against known? I mean, were you learning things that are kind of already known that, or is it possible to test that, against known interactions that might not be explicit in the training data?
We do a simple case study in our results, and the results show that maybe some of our recommended herbs are missed, but in practical clinical process, these herbs can be the optional herbs also.
Okay, I think, sorry, finish your answer, then we'll move on. Yeah, go ahead.
Because the TCM prescription itself is kind of ambiguous. Different doctors may give different prescriptions to the same symptoms.
Thank you very much. Sorry, finish your answer, then we'll move on.
So, I want to say that the evaluation itself sometimes is kind of hard to practice because it's an ambiguous question itself.
Is there anything else you want to add, or shall we move on? Thank you very much, Yuan.
Thanks, that answers my question.
Okay. We'll now move on to the next talk. While Yang Gao loads the talk, let me introduce the speaker. The paper is on PoisonRec, an adaptive data poisoning framework for attacking black box recommender systems. And the presenter is Junshuai Song, a PhD student from Peking University. His research interests mainly include recommender systems, reinforcement learning, graph data management and calculation, and big data-driven security. Let's go ahead with it.
Hello, everyone. This is Junshuai Song from Peking University. Today, I'm going to talk about our paper, PoisonRec, an adaptive data poisoning framework for attacking black box recommender system. Here's the outline of this talk. Recently, adversarial attacks raise serious concerns in the deep learning area. For example, in the computer vision domain, lots of works have shown that the trained deep learning models are vulnerable to adversarial attacks. In recommender systems, the same concern also exists. In this talk, I will answer a question like, can recommender systems be misled? If can, how? Data poisoning attack is the answer. Below is the simple pipeline of this kind of attack. For a data-driven recommendation algorithm, the attacker can control some fake user accounts to perform some click or purchase behaviors. If the model is trained on this part of data, it may be misleading. The question left is that, how can we construct effective attack samples? Before talking about existing attack methods, I will first introduce an attack example here for better understanding the data poisoning attack. On the right, there is a user item binary graph. Each edge with black colors means a click action that a user takes on an item. For the attackers, they can control some fake accounts to perform the click operation. If they frequently click a popular item chair and another target item hatch, then the recommendation algorithm may be misled that there are some connections between these two items. Users who have clicked or purchased the chair may receive hat in their recommendation results. Indeed, this is a representative heuristic attack method in the field of recommender system. To have better attack performance, there are also some learning-based methods, but most of them are particularly designed for given specific recommendation algorithms. And some of them require strong knowledge, like explicit user item interaction information when designing their attack strategies. However, we see that recommender systems with implicit feedback are more common in practice. And for security reasons, they will not disclose their system components, algorithm, and logs. In other words, they are usually a black box for attackers. And how to attack such a kind of recommender system is still underexplored. In this paper, we give a more effective solution for it. Here's the framework of our proposed method. On the right, we illustrate a simple recommender system, which mainly consists of candidate generation and ranker. And both of them are trained on the system logs. There may be other components like read rank, but we do not consider them here. For the date poisoning attack, attackers need to control some fake user accounts to take some click operations on the platform so that the recommender system can be misled and performs as their desires. In this paper, we focus on the item promotion task, where the attacker's goal is to make their own items receive much more exposures than before. Besides, it's clear that we need to explore discrete attack strategies, so we adopt the reinforcement learning as the core component of our solution. We formally define our item promotion task in this slide. On the right, there are some important notations that we need to know at first. I is the original item set in the recommender system, and IT is the target item set that the attacker wants to promote, which consists of 8 new items in this paper. N is the number of attackers, and tau represents an attack trajectory of an attacker. Each tau is sampled from a Poisson network pi theta. Then our goal is to maximize the reward defined on the set of tau. PoisonRec follows the reinforcement learning setting, and we introduce the state, action, reward, and the Poisson network in this slide. For convenience, we set the number of attackers to 1, and when we define these 4 concepts. For the state ST, we use the current attacker U and all the selected sequential actions so far to represent it. For the action AT, it means a sampled item that needs to be clicked at step T. For the reward, we use the total number of page views on the target items, which means how many times the target items are recommended to users. As for the Poisson network, we first use an LSTM network to embed the variable length state ST into a fixed length hidden variable AT, and then sample our next action based on the calculated multinomial distribution on the action space. This is the basic version of our solution, but it suffers from the low convergency problem when adopted in practice. There are mainly 2 reasons. First, the probability of sampling target items is very low, since the number of items in IT is much less than that in I. But we are trying to solve the item promotion task, where clicks on the target items are always needed. We cannot promote target items without clicking them. The second problem is that there is a very large search space. To solve the first problem, we view the necessary of clicking target items as a priori knowledge and propose a 2-step sampling process for it. PoisonRec first decides which item site to click and then choose 1 item from it. The sampling probability of target items increased to 0.5 in such a kind of setting. It could be seen that we build a 2-layer tree for sampling items. For the second problem, we solve it through hierarchical structures. we use complete binary tree here. It not only largely reduces the sampling time complexity, but also effectively speeds up the model convergency. This will be discussed later in detail. With the priori knowledge and the hierarchical structure, we propose our optimization, bias the complete binary tree, BCBT for short. On the left, the structure of BCBT is illustrated. To construct BCBT, we first build complete binary trees for the target items in I and the original items in I, respectively. Then merge these two trees with a new root. Each leaf node on the tree is assigned to real items in IT and I. The non-leaf nodes are simulated ones, and they are used to support our sampling process on the tree. And the difference BCBT brings is that the original sampling process of an item is split into multiple ones. I mean, a complete path from the root to a leaf node, where each leaf node represents a real item. When we update the sampling probability of the item A, all the nodes on the path should be involved. In such a way, the sampling probability of other real items that have the same ancestors with the item A will also be affected. This mechanism expands the impact scope of updating the updating operation for a single item, and brings us the opportunity to speed up the model convergency. If we can ensure such a kind of impact among items is positive, it will definitely help improve the model convergency. And so here we make an assumption. Items with close popularity have similar attack properties. With this assumption, when building BCBT, we need to first sort items by their popularity, and then assign them to the leaf nodes on the tree by order. In such a way, items with close popularity will be gathered together. If this assumption is true, the impact among items will be really positive and then can help PoisonRec converge much faster than before. This is a very simple assumption, but it does bring us impressive benefits when training our model. To sample an item, we need to sample a complete path from the tree, on the tree from the root to a leaf node. For the sampling process of a complete attack trajectory, it's like the decoder process for generating a sentence in the NLP area. For the model solving, we adopt the PPO, a popular reinforcement learning method. We normalize the rewards through a Gauss distribution, since they are usually large numbers each time. For the updating, we simply modify the original rules in PPO because we sample items from a tree and we need to update all of them each time. For other parts of this equation, they are the same as PPO. You can refer to our paper for more details. In our experiments, we adopt the 4 datasets and 8 recommendation algorithms. Based on them, we totally construct 32 different test beds to evaluate different attack methods. For the baselines, we compare PoisonRec with 4 heuristic methods and 2 learning-based methods. In the following, we will first show the effectiveness of BCBT and then report the comparison results with other attack methods. To study the effectiveness of BCBT, we compare 4 different types of designs. Plan is the basic version of PoisonRec, in which we directly sample items from the defined action space at each step. In B-plan, we only adopt the priori knowledge, which can help increase the probability of sampling target items to 0.5 at the beginning of the training. For BCBT popular and BCBT random, both of them follows the structure of BCBT. The difference is that we adopt the assumption 1 in BCBT popular but not in BCBT random. Here are some experimental results. These 4 figures show how the model converges with the training process when attacking item POP, covitation, PMF, and BPR respectively. For B plan, it has very low convergence. For plan, it has very low convergence. B plan always has a better performance than plan, which shows that it's necessary to build a best search space with the priori knowledge. BCBT popular converges much faster than others and always performs the best. For BCBT random, its unstable results clearly prove the rationality of our assumption 1. This table shows some results about the comparison with other attack methods. For the 4 heuristic methods, they perform not well. Another finding is that we cannot simply say which heuristic is the best. Different methods receive different attack results on different recommendation algorithms. For the 2 learning-based methods, PoisonRec still shows obvious advantages over them. Here is the conclusion. In this paper, we exploit the reinforcement learning technique and propose an adaptive data pointing framework, PoisonRec. Our experiments show that our method can poison black box recommender systems systematically and effectively. Thanks for listening.
Thank you very much. There's time for some questions. Questions, anyone? So are you planning to use this to target any real-life recommendation systems which are out in there in the real world? Have you tried it? Can't hear the answer. Can you unmute yourself, please?
Pardon, can you say it again?
Yeah. You have some results on test data. Have you tried it on any real-world recommendation system which is actually deployed?
Sorry, I'm not sure.
So the goal is to try to poison a recommender system, right? So there are a lot of deployed recommender systems. Have you tried it on any of them?
Yeah, we construct 8 different recommender systems in our experiments. And in this talk, we report some of them due to the time limitation.
And were the results on the other similar? Were it successful? Okay, maybe is there any other question? Okay. If there aren't any other questions, thank you very much for the talk. Again, we'll upload all the talks virtually because we are all muted. Thank you. Let's move on to the next talk. Let me introduce the speaker. This talk was on toward recommendation for upskilling, modeling skill improvements and item difficulty in action sequences. And the speaker is Kazutoshi Umemoto, who is a member of a research group led by Professor Masaru Kitsuregawa at the University of Tokyo, Japan. His research interests lie in information retrieval and data mining, with the primary focus on human factors and user behavior. Incidentally,
hello everyone.
Masaru is
I'm
go ahead.
From the University of Tokyo, Japan. Today, I'm going to introduce our recent work, which is about user action modeling toward recommendation for upskilling. This is a joint work with Professor Masaru Kitsuregawa, who is my boss, and Professor Tobamiro. this work was started when Professor Tobamiro was visiting our laboratory. So I'm very happy to present this work at the ICD conference this year. So let me first introducing the motivation of this work. So I think that practices are essential in our daily lives. When we are not expert, we don't know what action we should take at first. So in that cases, we experience trial and errors many times, and through those experiences, we can gain our knowledge, ability, or skills. For example, for people who are not good at cooking, like me, they first try very easy recipes. And after that, they will try somewhat more challenging recipes. And by repeating those processes, they can finally cook very complicated recipes, I think. And I think the same applies to many other real-world domains. For example, learning languages, playing musical instruments, and so on. So the one difficulty here is that we don't know what action is the best to improve our skills. If our action is the very easy one, we would not be able to improve our skills. On the other hand, if we try to take a very challenging task, challenging actions, then it's difficult to complete that one, and again, we would not be able to improve our skills. So can we develop information systems that can help people improve their skills? That is a question. And our answer to that question is that a recommended system that can upskill users, which is illustrated in this example, in these figures. And here, the skill level of this user is 3. And using that information, this recommended system finds items whose difficulty score is 3.3, which is slightly higher than this user's skill level. And by consuming these items, these users can improve his skills from 3 to 4. And this is what we want to achieve. And I think that to develop such a recommended system, there are three challenges. First, we need to understand how people improve their skills by selecting items. And this is the first challenge. And the second, we also need to estimate how difficult each item is. And also, we need to develop a recommendation algorithm that is suitable for upskilling. And in this work, we focus on the first 2 challenges and leave the last one for future work. Here, I briefly explain our problem definition. And we assume that we are given action sequences as given as input data. Here, each sequence contains the action that the user has taken in the past. And the action is represented as triplet, which contains the time, user, and item information. Here is meaning of items depend on the domains. For example, in the context of cooking, then recipes can be items. On the other hand, in the film domains, movies correspond to items, and so on. So for such given data, we address 2 problems in this work. The first problem is called skill improvement, and whose objective is determining the skill level of each user at each time when that user takes an action. In this example, from this time point to this time point, the estimated skill level of this user is very low, where the estimation, based on estimation, this user has improves his skills a lot at this time point. And the second problem we address is called item difficulty problem. Here we want to determine how difficult each item is. And in these figures, this item is estimated as easier than other 2 items. So from now on, I will explain how we address these 2 problems. So for the first problem, we use the existing progression models as a basis of our solution. And that model has its model has 2 ideas. First, it assumes that users having different skill levels tend to select different items. For example, in this figure, beginner users tend to select item I1 very often. On the other hand, that item was not selected by expert very often, and instead the expert users tend to select item 3 and item 4 more often. And to capture such a phenomena, we introduced the item selection probabilities as shown here, and this probability is conditioned on users' skill levels to reflect this idea. As another idea is done by progression models is that users' skill has some monotonicity properties. What it means that users' skills can improve as time passes, or it remains the same. However, the model does not allow the user's skill decrease as time passes. And this restriction is necessary to make the problem tractable. And using these ideas, we estimate the user's improvement process by mainly using the 3 steps. And as the first steps, we initialize the skill assignment of each user sequence. And this is done by first dividing each user sequence in equal size, as shown in these figures. And then we assign the lowest skill level to the first split, and second lowest, and we assign the second lowest skill level to the second split, and so on. And then in this way, we can obtain initial skill assignment data. Next, we use these initial skill assignments data to update the item selection probabilities. Then we use the updated item selection probability to update the skill assignment. Here, we try to find the optimal skill improvement path in this graph by finding a transition path which maximizes the joint probabilities of item selection of the target users. And then we go back to the, we repeat step 2 and step 3 until our model converges. However, the existing model has one problem. This is because in that model, the item selection probabilities describes only the item ID information, and this makes the skill estimation results unreliable, especially for items that doesn't appear very frequently in user sequences. So to address these issues, we consider multifaceted features that are shared across items. For example, in the context of cooking domains, each recipe not only has its item ID, but also has other information, other side information, like ingredient, cooking time, and number of steps, and so on. So in these models, in our models, we also leverage this side information when describing the item selection probabilities. And as I demonstrated later, this improves the robustness of our approach. Okay, now I explain our approach to the second problem. Our basic idea to solve the second problem is leverage the result of our skill models trained in the previous steps. And here we also have one more assumption that users typically select items whose difficulty levels does not exceed their skill levels. For example, we have 2 items here, and the left item is selected by 4 beginners and 2 experts. On the other hand, the right item was selected by 6 experts. So under this assumption, we can estimate that the left item is easier than the right item. And this idea is formally described in this way. That means that we estimate the difficulty of each item as the mean skill levels of users who select that item. And this approach is called assignment-based estimation. However, it does not work well, especially for rare items, which is illustrated in these figures. Here, there's one easy item, and this item is selected by a single user who is expert. In this case, our assignment-based estimation estimates that this item to be very difficult because only the expert selected this item. So to address these issues, we also propose another approach, which we call generalization-based estimation. Here, we estimate the difficulty of each item as the expected skill, not the average skill, an expected skill of users who are highly likely to select starter items. And formally speaking, this was calculated by using this equation, and it has two main components. One is the item selection probabilities, which is easily obtained from our skill models. However, another component, the skill flyer, is not available from our models. So we consider two approaches for this model to model the skill flyer. And one approach is just to use the uniform distribution. And the other approach is to estimate the proper distribution from the given data. And please refer to our paper for more details because I don't have enough time. So from now, I will report some key experimental results. In our experiment, we prepared 5 datasets, from which 4 were collected from real domains. And we also created one synthetic dataset that contains the ground truth information about user skills and item difficulty. First, I present the interpretability of the proposed models. Here, this graph is obtained from our skill models trained on the language domains, where we use the error correction count as one feature. And we can observe this graph that language learners with high estimated skills tend to receive fewer error correction. I think this makes sense. And also, we have another result here. This shows the common error correction patterns for language learners with low skills and high skills. And we can observe that the very basic mistakes like capitalization errors or missing function is only observed for the language learners with low skills. This also makes sense, I think. So in this way, we demonstrated that our skill models can capture the domain-dependent skills improvement very successfully. We also have more in that, but due to the time limitation, I will skip this slide. And the next experiment, we investigated the accuracy of our models. And here we use a synthetic dataset containing a ground truth information, and we compared 3 methods. One is a uniform, which is exactly the same as the initialization process of our skill models. And the second one is the ID, which is our base models, which relies solely on item ID information. And the last one is our proposed method. And here shows the result for the skill estimation problem. And we can observe that our proposed multifaceted works the best among all the baselines. And this shows the result for the difficulty estimation problems. We can observe from this graph that the combination of our multifaceted skill models with our empirical difficulty models works the best for this problem as well. So this demonstrates the accuracy of our model. Also, we conducted an experiment to investigate the usefulness of our models in practical recommendation tasks, where we addressed the latent prediction task using the BIA dataset. And we trained several recommendation models. One is a very basic model, just only use the user and item information. And we also train some other models just by adding skill information, difficulty information, and both of them. And we find from this table that adding difficulty and skill levels improve the recommendation performance, indicating the potential of our skill and difficulty models for the practical recommendation task. And we also conducted some experiments about the efficiency, but due to time limitation, let me skip this slide. And this is the last slide of my presentation. We addressed the problem. We addressed main problem for the building recommender system for upskilling. And I think it's time to stop. And thank you.
Thank you very much. That was a very interesting talk. We have time for a few questions. Anyone who wants to ask a question, feel free to unmute yourself and ask.
Hello?
Yeah, go ahead.
It's an interesting topic, and I noticed that you use several rating datasets, and I'm wondering what the meaning of skill and difficulty for user rating movies. Thank you.
Thank you for your question. I think the meaning of the user skills and item difficulty depend on the domains. And in the context of movie domains, we think that some movies requires users to have some experience levels. For example, for very light movies like Star Wars or Star Wars, then such a movie will be wider appealing for diverse users. But some classical movies like masterpieces, I think such kind of items should be not accepted by users who don't have much experience of watching many movies. I think such kind of concept can be regarded as user skills in the film domain.
Any other questions? I have a question here. It looks like something like this would be really useful in assigning problems to students of a course to help them learn and improve their skills gradually. Have you looked at this educational domain for applying these ideas?
Yeah, originally we are planning to apply our algorithm to such a domain, but we could only find one dataset for our experiment that is collected from the language learning website. But later we find that our problem setting is very similar to the some problems found in the educational domain. So we are planning to conduct some experiment using the dataset in those domains.
Would you know what kind of techniques they currently use for assigning problems with in those domains?
Actually, the problem setting is somewhat different because they use their problem is supervised settings. They use the actual feedback from the student who are taking some lessons. But such a domain called the knowledge tracing, and there are some dataset for that task. So we are planning to borrow some datasets from that domain.
Thank you. Any other questions? No? Last question, going once, going twice. Okay. Thank you very much. That is a very nice talk, and we'll applaud you virtually. You can't hear us applauding because everybody is on mute, but thank you very much. And thanks to all the other speakers. I believe that was the last talk of the session. After a half-hour break, we've actually finished this session pretty much on time. And so with the half-hour break, we have another keynote talk by Sharad Mehrotra coming up, followed by further sessions, including the session with the Best Paper Award. Look forward to seeing you there. Thank you. Bye. Hi, Yuanzan. I just came back to check on the status of room handover. So are you and Yang continuing to host the session.
Yeah, hi. So should I pause the recording or stop
Yes.
the recording?
Yeah, I think after this we have the keynote, I believe. So you might as well stop the recording because it's not going to be used for a while yet. And
Okay.
then after the keynote, we'll come back and open the room again. So don't hang up the room yet, but we will take a break